So I'm going to talk about, there we go. Okay, so I'm going to talk about how dimension reduction tools work. And hopefully, I don't know, well, you may have heard of TSNE, which is the most famous dimension reduction algorithm, or TISNE or UMAP, those are all very famous, those are both famous dimension reduction algorithms. And these algorithms allow you to understand what data actually looks like in high dimensions by projecting it down into 2 dimensions. So the input is high dimensional data and the output is low dimensional data that preserves something about the high dimensional structure of the data. So maybe the graph structure of the data, the local neighborhoods that are in the high dimensional data, or some aspect of global structure. Like, it's not really clear what they preserve, to be honest, but that's what they're trying to do, is preserve the high dimensional structure of the data. Now, dimension reduction, it turns out it has a lot of really important use cases, particularly in biology. So you want to, for instance, figure out if there are clusters, understand how these clusters are related to each other, create possible new features for machine learning. You could try to determine whether there are manifolds in high dimensional space that you didn't know about, like some smooth way to get from point A to point B in the high dimensional space. You might want to use these tools to find outliers or outlying clusters, or even just to determine whether you trust your data. It's basically a tool for exploratory data analysis. It allows you to kind of see inside high dimensional data. Now, I was lucky enough to get a chance to listen to Martin Wattenberg give a talk on how to use TSNE effectively. And he pointed out some really interesting things in his talk. First of all, that for TSNE, the hyperparameters really matter. If you fiddle with the hyperparameter, you can get completely different results. Like, this is the original data, it's 2D, the algorithm just had to leave it where it was, but it didn't. You fiddle with the hyperparameters and you get like these stringy things, or like the blobs go far away or closer, or it looks like random noise when it's actually just 2 separate Gaussian blobs. And then also he pointed out that cluster sizes in a TSNE plot don't mean anything. So if you have clusters that look like this, like a little one and a big one, and then again, the algorithm just has to leave them where it is. And if you fiddle with the parameters, it does all different things. And so, this is really, I've since realized that results like this are really a problem, because the biologists use these methods to figure out what's going on in biological data. And these problems are not supervised, so you don't know how to set those parameters. So you might easily get misled into thinking the data is one thing when it's actually another one. All right, so
people just use it with the default.
Let's see if we can mute. Okay, there we go. All right, so I ended up leading this working group at SAMC, and Yingfan, Haiyang, and Yaron and I, we decided just to devote a semester just trying to understand this topic. And here we are, we're still working on it 4 years later. Okay, so this is the Mammoth data set. It's a 3-dimensional data set. Our job is to project it onto 2 dimensions. It's like taking the mammoth and clamping it between 2 pieces of paper and crushing it onto the page like you would a leaf, right? Anyway, so that's the goal, is to crush it onto the page, preserving all of its little bits. Okay, it's like tusks and its feet and so on and so forth. So if we use TSNE and we change its parameter values, we don't get anything that really necessarily looks like a mammoth. So even if we crank up that parameter all the way, it still looks like a chicken at best. It kind of looks like it dismembered the mammoth and ran it over with a steamroller. And then this is UMAP, which is supposed to be an improvement over TSNE, and it doesn't really do that much better. It still doesn't quite look like a mammoth. Whereas this is LargeViz, which is supposed to be an improvement over UMAP. LargeViz actually does worse. And then this is TriMap, which preserves global structure very nicely here. And then this is the method that we produced, which is, I'll tell you more about it. It's called PacMAP, and it preserved the global structure of the mammoth pretty nicely. So that's a 3D data set where global structure was important. I'm going to switch to a much higher dimensional data set, which is the MNIST data set of handwritten digits. So it's like a few hundred dimensions. And here, local structure is important rather than global structure. So here, it's a very different data set, and you can see that TSNE kind of fills up the space. That's what it always does. This is UMAP. which does a beautiful job on this data set, preserving kind of these, separating out these clusters in the high dimensional space, where each cluster corresponds to a different handwritten digit. This is PacMAP, which did really poorly. Like if I didn't color these, you wouldn't actually know that these were separate handwritten digits. Like they don't appear as separate clusters. And then here's PacMAP. And this is our method. So what I'm trying to show you is that for both of these two very different data sets, PacMAP does well, even though kind of local structure, is important here and global structure was important for the last one. So one thing I want to point out here is that TS&E actually goofed this one up in terms of global structure. Like this is one handwritten digit, but it got separated out into two pieces. And this is another handwritten digit also separated out into two pieces, which is not what it's supposed to do. So hopefully you are starting to get the idea from the last couple of slides is that lots of methods have trouble with this balance of preserving local versus global structure. So local structure, what I mean by that is like the local neighborhood graph, like who your nearest neighbors are. For global structure, what I'm talking about is relationship between large things like clusters, right? Or respecting relative distances between points in the high dimensional space. Okay, so if you think about the different types of methods there for dimension reduction, there are like the methods go from like really global methods like PCA. PCA just does global, it doesn't do anything local. Whereas TS&E is like local, like focuses on local. As it turns out, UMAP also focuses on local. And what I'm hoping to show you during this talk is that PacMAP does actually both. It actually handles both local and global structure through different mechanisms. And I'm going to tell you about those during this talk. So just a little bit more about the history of dimension reduction, right? You think about where it started. So it started with global methods like PCA, like principal component analysis. And then right around the year 2000, things changed. Like there were all these methods that came out that were trying to do kind of more local stuff. So their goal was to try to preserve the distances between points when you map them down. Like the high dimensional distance should map down to a corresponding low dimensional distance. The problem with doing this is the distances in high dimensional spaces are really messy. Like sometimes they all look the same. Like it didn't really work. And then, so the first method that actually kind of really maybe almost figured it out was SNE, but it had a crowding problem where all the points would kind of glomp on top of each other. And so you couldn't really separate out which point was which. And so that's where the new generation of these methods came from, to try to really preserve the local neighborhoods, like who is next to who, but without the crowding problem. So, but these methods, they didn't really work like they were supposed to, as I showed you in the earlier slides. So that's why this whole literature arose, like, how do you use these methods effectively, right? The reason this whole literature kind of like happened is because these methods didn't actually work right, and it was really hard to tune the parameters. So you have all these papers that are like automatic tuning of the parameters, like how do we use this thing for transcriptomics and so on. And it's because it's like a little cottage industry of figuring out how to tune the parameters, which you wouldn't need to do if the methods worked correctly. So when we started working on this problem, we wrote down all of the equations for all the methods, like right next to each other, and tried to figure out, like, okay, what are they doing? So we put all the equations for all three methods, TS&E, UMAP, and PacMAP. So these are two local methods, and here's the global method. And we just stared at this forever and just could not figure out what was going on. Like it was almost like nothing was in common when you actually look at these functions. So we said, fine, let's just start over. Okay, let's just start over. We can't understand these equations. We'll just start from the beginning. So we'll start from the obvious, which is that if you have neighbors in high dimensional space, we should attract them when we put them in low dimensional space. They should be close together. And if you have points that are far in high dimensional space, they should be far in low dimensional space. So we should repulse them, okay? So you'd think, all right, that sounds like a reasonable thing to do. Let's give it a try. But as it turns out, that is not enough to maintain global structure. So I can put together an objective which says attract my neighbors and repulse the further points, like, push them apart. And then I can do that, and I can minimize this objective and do a great job minimizing this objective and still completely lose global structure. So here's an example. So this is a data set where all the points are along this kind of funky curve. And then I take this and minimize this objective. Again, all I have to do is leave it alone, but that's not what happens. Instead I get this thing like this. And here, again, I've made sure all my neighbors were next to each other and all my further points were far away from each other. So I've optimized this perfectly, but I completely did not maintain global structure. So there's something wrong with this idea, right? It's not enough forces. So after a huge amount of experimentation, we found that certain specific properties of the loss function are important for local structure. And the choice of which graph components to exert forces on is important for global structure. So let me explain what I'm talking about here. So all of these algorithms minimize an objective that looks like this. It's a sum over graph components, which are like pairs of points or triplets of points. And then it's some kind of weighted loss for that graph component. Okay, so all the methods do this. Now, if you want to get good local structure, then you should really care about what this loss function is. And if you care about maintaining global structure, it turns out there's a different mechanism that governs it, which is what this sum is over. Which graph components you're actually going to work on preserving when you project down. Okay, so let me describe, the next sort of bulk of the talk is sort of describing these two pieces in detail. So first I'm going to talk about the local structure piece. So how do you maintain local structure? Now for local structure, we need to talk about the loss function. But I can't really write down an equation that's similar to all the loss functions because all the loss functions have completely different functional forms, right? They are very difficult to figure out. Like trying to find something in common with these crazy functions, that is not fun. But we did figure out a way that all the functions are similar. And it doesn't involve equations. It involves a figure. And we called this figure the rainbow plot. So the rainbow plot is a way to visualize and understand the loss function. So let's say you take a triplet. So I, J, K, I is you, J is your friend, right? J is your neighbor, and K is a point that's far away from you in the high dimensional space. So K is like your enemy, okay? So you got you, your friend, and your enemy. Okay, here they are. And your goal is to keep, when you project down, your goal is to keep your friend close to you and you push the enemy away, okay? So this is a plot of the loss function. It's like a heat map of the loss function. And then this here is the distance to your friend, and this is the distance to your enemy. Now, where you want to be is over here, because that means your friend is close and your enemy is far away. So that's where the loss function is low. Okay, and then the worst scenario is when you're over here. So that's when your enemy is really close by, but your friend is like nowhere near to help you out, okay? So the loss function is large over here. So what about the rest of this thing? Okay, so what about over here? So what do we think the loss is over here? So here your friend is close to you, but your enemy is also close. Now, as it turns out, for all of these loss functions, that is bad. So anytime your enemy is close to you, that is bad, even if you have a friend close by. Okay, and then what about this? So over here, this is where your friend and your enemy are both far away. And it turns out that this, believe it or not, is actually okay. This is like, you're like, yeah, I'm cool. Even though I don't have my friend close by, we're good, okay? All right, so let me fill in the rest of this plot for you just to show what it looks like. So anytime your enemy is close to you, that is bad. As long as your enemy is far enough away, you're okay. You're happier when your friends are close, but if not, that's okay. You're all right. Okay, so I'll fill it in even more, which looks like this. So this is the rainbow plot, and see it's red down here when the enemy's close, and dark green here when your friend is close instead. This is the magnitude of the gradient over here. Okay, and I could say, and you could say, well, which loss function is this? Is this TS&E's loss function? Is this UMAP? What is this thing? And the answer is, I don't know, because they, believe it or not, even though they have totally different functional forms, they all have the same rainbow plot. So this is TS&E UMAP, this is PacMAP. The one that's different is TriMAP, but remember, TriMAP does not actually do that well in terms of local structure, kind of crams all these things together. So the ones that are good for local structure tend to have these rainbow plots that look like this. Okay, so once we figured this out, we developed some principles for what a good loss function should look like for preserving local structure. So I'm going to show you, I'm going to walk through the principles one by one, and I'll put the formalizations up, but if you want more detail, you can go to the paper. But basically, the principles are shown in this kind of diagram over here. Okay, so the first principle is monotonicity. So you want this plot to go up and to the left, because you want your enemy to be further, your enemy should be further away, your friend should be closer to you. So that's all this says. So it just says push your enemy away, make your friends, pull your friends in. Okay, that's it. The second principle, there. So up and to the left. The second principle is that except at the very bottom, the gradient should go mostly to the left. So as long as your enemy is like far enough away from you, you should be kind of gradually pulling your friends toward you. You should exert like a gentle force on your friends. Okay, so things should go mainly to the left. And we've written everything in terms of derivatives just so that everything's scale invariant, because the gradients are just compared to each other. So you can scale the loss by whatever you want, and the principles are still okay. All right, so gradient goes to the left. Third principle, at the bottom, the gradient goes up. So you should push really, really hard on your enemies. Make sure they stay away from you. Don't want them next to you. Okay, so those are those three. Keep going through the rest. Fourth one, at the very left, the magnitude of the gradient is small. Okay, and that prevents you from the crowding problem when all the points go on top of each other. So as long as your friends are like close by, you stop pulling them in, because otherwise they'll smother you. They'll be like right on top of you. Okay, yeah, so there's a light color there. Now at the bottom, the gradient always has a really large magnitude. Like you really, if your enemy gets too close, you really want to push them away. Like that's not cool if they're nearby. All right, and then the last one is that the gradient should fade as your neighbor gets further away. So you should just give up on neighbors when they're too far. So it's like, my friends drifted away. Bye, friend, I'm sorry. See you. Okay, so yeah, you should have this gradient that looks like this. So no gradient when they're really close, high gradient when you can pull them in, and then just kind of give up gradually as they get further away. All right, and that's what gives us these nice rainbow plots. Okay, so while we were doing this, we tried to come up with some loss functions that looked like they might be good on the surface, but they turned out not to be. And you can tell that they won't work by looking at the rainbow plots. So here are the results of all these loss functions we tried. They were disasters. And then here are the rainbow plots, and you can see that the rainbow plots just don't look right. Like they're, the first one, it doesn't go up into it mostly goes up and not to the left, right? And there's no force on the enemies. And then here again, you just don't have sufficient force on the enemies like when they're nearby over here. On this one, we have nothing pushing the enemies away. And here, this one, again, it just doesn't look right. And so you're not seeing good results here. And that's what you'd expect. All right. So once we had the knowledge of what a good loss function's rainbow plot ought to look like, we could actually design an algorithm that had a sort of perfect loss function according to the rainbow plot. So PacMAP has actually a very, very simple loss. It has 3 terms, one for friends, one for enemies, and a third one that I haven't talked about yet. So we define just the distance between 2 points in the low dimensional space as being their Euclidean distance plus 1. And the plus 1 is to prevent division by 0. Okay. And then the two of the 3 terms look like this. So the neighbor term says pull your neighbors in. The further points term says push your further points apart, and it literally this is it. Like none of this complicated stuff. This is what it is. Okay, so it's like this distance over distance plus 10, and then 1 over distance plus 1. So this thing encourages the distances to be small. This thing encourages distance to be large because you're repulsing. And that's, that's literally what those terms are, right? Nothing more complicated than that. Okay, so that's how PacMAP deals with local structure. The third term I haven't told you yet. This one deals with global structure. So now I'm going to switch over to talking about global structure. So as I mentioned earlier, we have this issue that there are just not enough forces if you attract your neighbors and repulse further points, okay? So it's really problematic. It's really problematic, and it affects UMAP and TS&E really badly. In fact, this result, where it just was supposed to leave this alone, but it didn't, this is actually a result of UMAP. And UMAP is one of the algorithms that's very nearsighted. It just doesn't have enough forces that, you know, it only has forces like these two, and it doesn't really handle global structure well. So here, for instance, you can see the force as a function of distance, and both attractive and repulsive forces fade very rapidly over distance. And so what happens is that you just don't get like the global structure being preserved. So Yingfan had this really neat idea, which is let us attract mid-near points to maintain global structure. So a mid-near point is not a neighbor and it's not a further point. It's something that's kind of mid-near, right? So let us attract, for this point, let us attract points that are a little bit further away, okay? So that we can maintain kind of global structure. All right, so PacMap's loss, and I can now give you the full thing again. The full thing with the third term has these three terms. The first two I told you a minute ago. And the third one is actually a gentle attractive term. So it's very similar to the neighbor attractive term, but it's a little weaker over here. And these parameter values don't mean anything. It's like a 1, a 10, and a 10,000. It's not sensitive to that. You just kind of get the kind of like idea there. And it, you know, once you have the idea, it doesn't matter exactly what parameters you put in, it's going to work. Anyway, so the mid-near pairs, okay, what are those? So the mid-near pair for sample I, to get that, you sample 6 observations from the data, and you choose the second closest of the 6, and that's your mid-near pair. Then you pair that with I, and you gently kind of pull it in. And so this allows you to kind of to really get global structure preserved. And it really does matter. So here's a data set, which is a S-curve with a hole in it. It's a 3D data set. And if you don't have any mid-near pairs, you can't preserve global structure. But if you have even 2 mid-near pairs per data point, then you get the global structure. And then, you know, it doesn't, you know, as long as you have at least 2, okay? And then here for the mammoth, if you don't have any, you get garbage. If you have at least 2 mid-near points, you get that global structure. So it really nicely preserves the global structure. So the way that PacMap is trained with this loss function, now that you know what it is, it's trained in 3 stages. And those 3 stages kind of, the first stage really pushes on global structure, the second weakens global structure, and the third removes it so that you're looking only at local structure. So you really kind of like vaguely, like you just got to put the points in the right locations vaguely, and then kind of get the local structure fine-tuned afterward. So the weights, these weights, so these W's, they change on a schedule. In the first stage, you basically just handle mid-near pairs. So it's like let's just mid-near pairs, just get the global structure sorted out. And then you weaken the mid-near pairs in the second stage. And then in the third stage, it just goes away. Like you're only doing at that point local structure, neighbors, and further points. Yeah. And then we use just plain old atom optimizer on the loss function. So there's nothing special at all about the way that we're optimizing it. And then if you look at what's happening with PacMap over iterations, you can see what's going on. Like in the first stage, it's really sorting out global structure. And in the second stage, it's kind of getting like fine-tuning that global structure and then starting to work on the local structure. And then in the third stage, it really hammers on the local structure to really get that local structure looking nice. And that's how it works. So now I've explained to you kind of what makes these dimension reduction methods tick, and then, great. So then we designed PacMap, but we ran into this issue after we designed PacMap that we couldn't figure out how to evaluate it because this is all unsupervised. So how do you evaluate these things? So we thought about it, and by the time we finished thinking about it, we ended up having to just write a paper about it. So we actually wrote a paper called, how do we evaluate dimension reduction algorithms? And we did it for transcriptomic data visualization. So we provided a whole series of metrics you can use to evaluate dimension reduction. The first is a local structure method, where you take supervised data, you project it down in an unsupervised way, and then try to classify it and see if you can classify well. So if you can, it means you preserved the kind of class structure when you did the projection. Then for global structure, we proposed triplet loss, which is you have 3 data points, try to make sure that, and you have your neighbor, and for the point, if the neighbor was, well, if you have 3 points, if the second is closer than the third in high dimensions, well, that relationship needs to be maintained when you project. And then sensitivity to parameter choices. You don't really want your method to have a different visualization when you change the parameters. Also sensitivity to pre-processing choices, as well as computational efficiency. And PacMAP does well in all of these metrics, but I don't really like showing tables in talks, so I'm just going to do a bunch of demos. All right, so we're back to MNIST. And so to measure the local structure, you would take the dimension reduction projection, like take all these projections, and then put the class labels back in like I did. And then you'd run a classifier on this and the 2D projection to see if it can separate the classes. And here in this visualization, all of the methods would perform well. Because even if these are separated into different classes here, you can still run a classifier and do a good job classifying, right? This is a global structure failure, not a local structure failure. So, so all these methods would do well in terms of local structure. Okay, so then this is the example for global structure preservation again. Here, our friend the mammoth. And so here, large viz would do really bad on the triplet loss, because any triplet involving one of these points, it might not be, that triplet might not, the relationship who's closer to who, that might not be preserved when you do this large viz projection. So here would be, you would see some failures. Also here, you'd see some failures in global structure. And so here's a bunch more data sets with more of the same kind of thing. So the coil data sets are actually, they're just coils. And then this is MNIST again. This is fashion MNIST, which is like handbags and shoes and stuff like that instead of handwritten digits. And you can see again, this is another local structure data set. So PacMAP and UMAP perform very similarly on this data set, which is good because they're both good for local structure. This is another handwritten digit data set. This is a newsgroup data set where nothing does well because apparently newsgroups tend to overlap a lot. So yeah, this is the S-curve of the whole. And you can see the methods, like TSNE and UMAP just fail miserably on these methods because they're so nearsighted that they don't get the global structure. And this data set is interesting. It's a mouse RNA-seq data set. And a biologist might look at something like that and get really excited because they're seeing lots of clusters, but they're probably just phony. I mean, you can see based on these plots that these clusters are probably just artifacts of the dimension reduction method. So that's a danger of using these DR methods that don't maintain global structure. So here's a data set that, this is a visualization by Carla, who's been working with us from a lab in Germany. And she visualized this peripheral blood mononuclear cell data in colored it 3 different ways. So this is colored by cell type. And you could look at this here. Okay, so that's why these 2 clusters are connected, because they have the same cell type. And then, but they're different because they have different experiments. And yet they're also the same method. So that's why they're kind of off by themselves. So you can kind of really get a sense of what's going on by visualizing all of this, all of these data. And I'm going to show you the same 3 images with UMAP as the method for producing these. And it's just not nearly as clean, and you're not really seeing the global structure as well as you did with PacMAP. Okay, so let's go to sensitivity to parameter choices. So what you don't really want is clusters kind of splitting off and doing other things. Like you really want the global structure to be robust to parameter choices. And we already knew from the very beginning of the talk that TS&E doesn't have that. So here, for instance, these two bits of the same cluster are in totally opposite sides of the DR plot. And then if you change the perplexity, all of a sudden they end up together. And then same thing for UMAP, like they're apart, they're together, they're together, they're apart. Okay, whereas TriMAP, which handles global structure, always has them kind of relative to each other in the same way. And PacMAP also always keeps them together. Okay, and then pre-processing. So a lot of people, since these DR methods don't scale to an infinite number of features, what people do is they take their like maybe 2,000 dimensional data set and they project it using PCA to 100 dimensions. And then from there, they use the dimension reduction methods. And so you really don't want your choice of how many principal components you preserved to be relevant to like what the DR plot looks like. So this is an example where, you projected down to 30 principal components versus 100, 50, 70, and 100, and it should all look the same, but it doesn't. Like here it separated them out. Here they're together, separate for different, like, just an innocent choice that shouldn't affect global structure. Whereas again, TriMAP, completely robust to global structure, same with PacMAP. Now the last analysis is runtime. So I'm going to show a table. Sorry about that, but it's very easy to read because PacMAP is just much simpler than all the other methods, and so it just finishes in a much faster runtime. And it even finishes on cases when the other methods can't run because it would take too long. Okay, so let's finish up with a couple more applications. So I'm going to start with an application to name ethnicity classification. So now that we have PacMAP, right, we use it for everything in my lab, right? We're using it for all the data sets new data sets that we're coming across now because we want to see what's in them. Anyway, so this is a name ethnicity classification project. This is helpful for assessing fairness. And the idea is that you don't actually have race or ethnicity information in your data set, but you have people's names. And so you can try to deduce whether your method is being fair by deducing the ethnicities from the names in the data set and then checking to make sure your algorithm is doing well on the appropriate fairness metrics. So we developed this algorithm called Ethnicia, and we developed a set of features that are useful for predicting ethnicity from a name. And we took those features and projected that space down to 2 dimensions and plotted, using dimension reduction. So each point here is a different name. And so what you're seeing is the space of names, okay? I think it's pretty cool to see the space of names like this. So here you've got kind of Spanish names, Asian names, these are Black names, and these are white names. And an interesting thing that you see here, and this is voter registration data in the United States. So one interesting thing that you're seeing here is this blend between Black and white. And this is because the slaves took the names of their owners, like the last names of their owners. And so you see this big kind of mix between the Black and the white names over here. All right, and then this is an application to EEG monitoring. So this is if you are, let's say you're critically ill, you got into a car accident or you have a stroke or something terrible and you ended up in the hospital. You have EEG monitors all over your head, and they're checking for kind of seizure-like activity in your brain, which the doctors are trying to protect you from. And so we built a interpretable neural network for EEG, and so what I'm showing you here, this is an EEG signal that we're trying to classify with this neural network. And the neural network picks out kind of neighboring signals that are similar to that one to kind of show the user what's going on. And then this is a PacMAP projection of the EEG signals, of all the EEG signals in the database, down to 2 dimensions. This is like the latent space of our interpretable neural network. And what you see, besides an interesting, rather funky sea creature mixed with tadpole type of thing, is that each different end of this is a different color. And these correspond to the different types of EEG signals. So these are seizures in red, LPDs, GPDs, Lerta-Gerdes, and so if you walk kind of around the sea creature, you can go between the different types of seizure-like activity. And the doctors really enjoyed seeing this plot because they, you know, it shows that there's a continuum between different types of EEG signals. It's like they're not like separate clusters. There's actually something that kind of walks between them gradually and smoothly. So they've been using it for like educational purposes to walk from one type of EEG signal smoothly to another. Okay, and the last application I want to talk about is the FICO challenge dataset. So this was the dataset used for the Explainable Machine Learning Challenge. It's a home equity line of credit dataset. You're trying to predict based on someone's credit history whether they're going to repay a loan. Now, the students who are working in this project named PacMAP. I did not name PacMAP. They named it. And I kind of looked at the name and I was like, like, not my favorite name. Like, it sounds kind of like Pac-Man, like a cartoon character, like or a video game character. Like, who cares, right? You know, not my favorite name, but they named it. It's their algorithm, so they get to name it, and that's fine. Okay. So I emailed UniV and I'm like, hey, can you send me the result for PacMAP on FICO dataset? Just send it back. So she sends me this figure, and I'm like, no way. Like, it's just not possible. So I couldn't believe it. I just thought, how is it possible that PacMap produced Pac-Man? Like, how is it possible? And I said, are you joking me? And she said, no, there's actually a reason for this. She said, actually, you can kind of explain it. Like here, for the thing he's eating, like that's actually the parts of the data set with missing pieces, like missing features, and then this part they have higher external risk. Like you can explain it. Actually, this is actually what's going on in the data set. And you know, it's sort of mimicking what we see in our models, to be honest, on this data set. But anyway, I find this kind of exploratory data analysis really useful because it really tells you something about the clusters or the manifold structures within the data. But for this result, it's kind of hard to take that result seriously. All right, so just to summarize, I talked about what makes dimension reduction methods succeed or fail. And in particular for local structure, I talked about the fact that you need a good loss function. And I talked about what makes a good loss function. It's obeying the 6 principles. You should also check the rainbow plot. The rainbow plot is useful because it allows you to compare across algorithms. Okay, there's our rainbow plot. And then for global structure, you should include forces on non-neighbors, which is why we use the mid-near pairs. And that the fact that these were 2 separate mechanisms allowed us to get both local structure and global structure without sacrificing either one of them. So we introduced PacMAP, which is a very simple loss function involving 3 terms. It has very simple weights. It preserves both local and global structure. It has fast runtime. And hopefully it'll give you some information you can glean about what's actually in that high dimensional data so that you can be a responsible decision maker. And so what I have here are just the papers. This is the PacMAP paper. This is the GitHub repo. It actually has 260 plus GitHub stars right now. This is a slightly old slide. And then here's the paper that we wrote on evaluating dimension reduction methods. All right, thank you very much.
Thank you for this wonderful talk. So now it's time for questions from our audience. So there's one question in the chat box. Why did you use Euclidean distance over other metrics? Do you find any issues with its use in the high dimensional space?
So that Euclidean distance that I showed you was in the low dimensional space. So that's the 2-dimensional space that you're visualizing. For the high dimensional space, you actually have people figure out their own distance metrics. So you have to, you don't have to use Euclidean distance in the high dimensional space. It's just in the low dimensional space that it's important there.
Yeah, so following that question, may I ask what is the distance metric you use for the high dimensional space?
Oh, it depends on the problem. I think most of the time we're using some kind of just normalized Euclidean distance, but you can use like, whatever. We've tried all kinds of weird distances. We've tried distances where you walk along a graph. I forgot the name of that type of distance. We've tried all kinds of weird distances. Yeah.
So I also have a question. So may I say that your PacMap method is the only one that uses the 3 parts in its loss function by considering the mid neighbors?
Yeah, I don't know any other methods that do this kind of thing, although we've started to get some queries from kind of the designers of UMAP, so I don't know what they're planning to do. But yeah, our method's the only one that I know that does this three terms thing to ensure the global structure. So there's a question in the chat, which is whether there's an R package. So we've been trying to develop an R package, but we've had a lot of trouble doing it. It's technical trouble doing the conversion from where we are right now to R. So if any of you are just amazing R programmers and know how to help us, then we'd love to talk to you. But these challenges are quite technical and quite difficult.
And there's another question. Does PacMap provide any variable loading information similar to a PCA?
Yeah, so that's a good question. So yes, so you can initialize with PCA, and that's actually what makes TriMap work. So like and UMAP, because those methods don't actually optimize global structure, so they kind of rely on this initialization using PCA to actually get their global structure. And PacMap doesn't need to use PCA as initialization, but it definitely makes things faster because PCA sort of plops everything into kind of a reasonable place globally. So we do use PCA initialization, yes.
And so how you showed a plot showing that PacMap result is not sensitive to the number of PCs you input, right?
Right.
Yeah, and my question is how sensitive it is to the number of mid neighbors you specify for the second term.
It's not that sensitive as long as you have enough. Like if you have 0 versus 2, then that's going to be a huge difference. Like I showed you a figure where it's like 0, 2, 4, 6, and the 2, 4, 6s all look the same, but the 0 to 2 does not look the same at all. So as long as you have like sufficient global structure, then you're going to get something reasonable.
Great. So
and I should mention that we've been trying to improve over PacMap for the last couple of years. Like we published that paper in 2021, and this is 2023, and we've been trying to improve it since then. And we have not found anything better than it. And we've been like actually, spending like a lot of time every week working on to try to improve it, and we haven't been able to really do it very well. So yeah, so it's pretty robust. It's pretty robust. I mean, you can fiddle with it a little bit on like there's certain data sets where like if you have a really tiny data set in 2 dimensions where global structure is really important, then maybe PacMap won't get it, something like that. So in that case, you might want to, fiddle with the parameters a little bit. But for most high dimensional data sets, it's really quite robust.
And yeah, so back to the POET example in that how to effectively use t-SNE block, I'm curious how PacMap would look like if you apply that to that simple 2-dimensional Gaussian data, like 2 components on that one.
Oh yeah, we haven't tried that, but that data set it would work fine on. I'm not worried about that data set. I mean the cases where it's failed are like just so you'd never use a dimension reduction case for that type of data. You know what I mean? So like points that are in a specific location in 2D space or something like that, where
Yeah, I see.
Yeah. I mean, another case where it's very, very difficult for any dimension reduction method to work is like when you have clusters within clusters within clusters. So if you a big cluster, and then within that you have several small clusters, and then within that you have several small clusters. It's very hard to get any method to kind of get all this hierarchical clustering kind of correct.
That's not a 2-dimensional, right?
Yeah, something like that. Well, it's a high dimensional mixture, and you want to project it down to preserve all that stuff. It's very difficult to do it.
Yeah, there's another question. Any comments on embedding new data into the existing 2D projection?
So, okay, this is we had a long conversation about this with one of our users. So our users kept asking us to do this. And so my students and I were like, why are you asking for this? Like, we don't understand. Like, why don't you just retrain it? Like, it's very quick to retrain it. So it doesn't make any sense. So we were kind of fighting back with one of the users who gave us some really kind of useful insights, which was like, well, I don't want to retrain it. I want it to be consistent with what I had before. Just kind of like interesting, like the way people were using this stuff. And so we actually do have a capability of, in the current version of PacMAP, we actually do have a capability of embedding a new data point into the existing 2D projection. So you can go ahead and do it. I still find it very weird.
I see. So actually, regarding the running time, do you have the computational complexity of your PacMap versus other methods in terms of like N and D?
Well, I mean, you can't exactly, it's not, I mean, I guess you could compute per iteration, like compute, because it's gradient descent, right?
Mhm.
I mean, it's very, very fast. Let me go back to the objective function so you can see. So the hardest part is, let's see, share again. So the hardest part is just computing all these graph components, right? So once you compute the graph components, you're literally like doing gradient descent on this loss function. So it's like almost, it's just so fast. So if I go back to the like the timing plot, like this is showing you how big the data sets are. So 20,000 points, you're doing it in 13 seconds. You see what I mean? So this is 4 million. We took us 2 hours.
Wow. Yeah, I'm just curious, like, do you think the magic for this faster speed is due to the loss function or is it due to implementation?
It's definitely not due to implementation. Yeah, it's definitely the simplicity of the whole formulation. Yeah, I mean, I'm not saying that we are I'm not saying we're the worst implementers. We're pretty good, but we're having enough trouble, as you know, getting things into R that that we're not the most amazing R programmers or whatever in the world. But yeah, it's just due to the formulation. It's just the simplicity of it.
Yeah, and Sushmita that has a question. So there's no tuning parameter of your method.
So there are an infinite number of tuning parameters in every method. You can always plop a parameter somewhere and like tune it. So like for all of these methods, you can tune anything. Like for us, for UMAP and TSN, you've got a gazillion of them, but the perplexity parameter, it's very, very sensitive to that. For us, it's not sensitive to anything, but there's a lot of parameters, right? There's the 3 stages, like when do you change from one stage to the next? What are the weights? There's 3 weights, one in each term. How are you, linear pairs is like the second out of 6, like, okay, you could do the second out of 10 or so, so there are a lot of parameters, but it's not sensitive to any of them, which is the important bit.
Yeah, and for that robustness, we don't have theoretical understanding of why yet, right? We have the empirical evidence.
Yeah, I mean, I don't think you can really. Yeah, I mean, this is all. Yeah, it's not like a mathematical proof that you can do for the for the other types of problems that that I'm working on. I mean, this is an unsupervised problem, so unsupervised is always a little funky. So usually you do it with like some Bayesian derivation. If you're working on an unsupervised problem, it's usually either doing something Bayesian so that it's principled that way, or if you're supervised, you can minimize a loss function and get kind of mathematical proofs of optimality with respect to the loss. But for dimension reduction, that kind of it's unsupervised, so you're back in the case where there's no correct answer. And so we derived a loss function that seems to work. It preserves things like neighbors, further points, and linear pairs, which we think are reasonable. But yeah, there's no like mathematical theory saying that's the right thing to do. And if you know of any like honest to goodness like mathematical theory telling you exactly what to do, they would have solved the problem. And I can tell you right now that doesn't exist.
In Michelle, suggestions on best practices for using PacMap for cluster analysis and classifying the cluster of new data point. So she's asking for suggestions for practical use.
Yeah, so that's exactly the kind of thing that we're using it for, right? So you run PacMap, and then you can take a look at the clusters and see if the clusters are actually meaningful for anything. Like if you discovered that, like for example, we have the single cell data right now where part of a known cluster seems to have broken off and attached to something else. And so we've been trying to figure out if PacMap is right or if the original clustering was right. And the more we talk about it and like talk to the domain experts, we actually think PacMap was right in separating this into two pieces. So like it's actually completely it's like a really quite excellent use case.
Yeah, actually, speaking of that, I think there are another category of dimension reduction methods that try to make the cells look like following a continuous path instead of falling into discrete clusters. So I think they are kind of adding their assumption, a global structure before they do this dimension reduction. Did you consider comparison with those?
So the problem with methods like those is exactly what you just said. Like you're assuming that there's a continuous manifold in the high dimensional data, but you don't know that.
You know that, yeah.
The idea is that the method, if it's properly preserving global structure, you shouldn't need to put your domain expertise in to tell it that. It should figure it out. So I think that methods like that are just they're not doing what we know is the right thing to do. So I'm not too keen on that. I know a number of people have kind of proposed various things to me that also kind of like insert a bunch of domain expert knowledge that might not be correct, and in fact generally are not correct. And so I've just been kind of like, no, I'm not sure I want to work on that.
Right. So any further questions from our audience? Yeah, this is very insightful, especially the 6 principles you gave. I think that's kind of, make things more, in one place, because otherwise people may say different things, but they're not unified under principles.
Yeah, so at least we got that far. I want to point out that my students, Yingfan and Haiyang, they are absolutely amazing, and they've been so good to people who write to them. Like if they have, like I said, like they have 260 GitHub stars on PacMap right now, and I think the reason for this is because they've been so good at answering people's like questions from users. So if any of you have like questions, or if you want to try using it and you have any issues with it or whatever, like we want to know, right? So yeah, so we want to know about your experiences using it. So please let us know if you could decide to give it a try. And yes, I'm happy to give you a copy of the slides if you want it.
Oh, that will be very helpful. I think the WNAR will also post the slides along with the YouTube link on their webpage. And so, give a copy. Okay, I see the question. So regarding the graph components, right? You said that's important for the global structure. Can I say that in your loss function, the graph components are neighbors, and the whole thing? So and the far neighbors. Sorry, I'm saying that how can I summarize or can I list the global graph components you use to make your loss function work or better?
Right. So there's 3 kinds of graph components. One is neighbor pairs.
Yeah.
IJ pairs, and then one is further point pairs.
Yeah.
And then the other is mid-near pairs. So those are all the graph components.
So are they? If you pull them together, do you include all the nodes? I mean, like the further nodes, are they the ones that are not considered as mid neighbors, or do you leave out some of the nodes?
Oh, you leave out. So you can't include all the pairs. So you just use 10 pairs, 10 of each type.
Oh, I see. Yeah.
And you can, that's another parameter that you could adjust that doesn't matter.
I see. Oh, I think that's probably, but for the pairs, you include everything, right? So for the pairs or no, you have to rely on a graph or some way to start with graph.
Yeah, so the whole problem has to be, there has to be some graph that determines whether you're a neighbor or further pair
Pairs.
forming. So you have to start with some, yeah, you have to start with some kind of a graph or distance metric in a high dimensional space.
I see. Yeah. Okay, so a question. Yes, we will post the recorded talk to the YouTube channel. I'm posting it here so everybody can have that. Everyone meeting. Yeah, this is the YouTube channel of WNAR webinars, and it will be posted shortly after we have the recording. Thank you. All right, so Cynthia, I think this is great work, and I'm very happy that you shared it with us during this webinar. So we really appreciate your time.
Yeah, thank you for inviting me.
Yeah, and hopefully PacMAP will be a useful tool for the field. And if everyone has any questions, please feel free to let Cynthia know. I think she must be welcoming users.
Definitely, definitely.
Yeah. All right, so thank you, Cynthia, and thank you, everyone. So we'll see you at the next webinar. See you. Bye.
Bye, thank you.
Bye.